Good afternoon, everybody. I hope you can all see me. I hope you can all hear me. Here's my first request. Please mute yourself, because if a lot of people are talking, you cannot hear me anymore. And of course, I would like to do this presentation. So please mute yourself. I see still some people talking. Thank you. So first, a small check. There is a raise hand function in WebEx. And if you can hear me, can you please raise your hand? And I can see that here on my screen, raising your hand. Yeah, I see 2 people, 3 people raising their hand. Thank you so much. Okay, so we can start today. Again, double check if you're muted. And then
Vielleicht kenne ich das irgendwie.
Webinar
Noch mal,
about
weil wir haben ja
functional
so viele
safety,
Themen, ne?
an introduction to PESS. As you know, the last time we had a lot of people in our meeting, so much that our servers could not handle it anymore. So we updated everything, and this is a special redo of last time. Let's start with the first slide. First things first. So, who am I? My name is Simon Moleman. I'm your host today. As you've probably seen, I'm on a different account. It's from my colleague. As you know, Licht Institute is a Dutch company, so I'm Dutch as well. I'm an electronic engineer. Also, I'm a functional safety engineer. And I'm a product specialist engineering. So my main specialties are 2 standards. One of them is 62508, the lead standard for functional safety or electronic safety systems, and 13849 and EN 13849 machinery. So you can see I do machines, I do lifts. Check yourself if you're muted or not, because if we have too much people talking, we cannot hear each other anymore. So please mute yourself.
You have to mute us.
Also, the author of the article "Why PESS is not PESS." You can find this article in the Elevator magazine. The URL. I did certification for Mitsubishi. The SET system, which is for large high-speed lifts. And also machines, for example, CBESS, which is a platform lift. It's also a fully electronic safety system. In this webinar, are appreciated. However, we have your microphone. And for all your around, send them to contact. Second thing, your microphone muted. This is the 3rd time. If you have a question,
Settings.
The chat is. I will invite you to use the chat.
Go to setting.
I already typed the question with the number of the sheet in the chat. I have to. Okay, I have to mute you all. Give me a second, because so give me a second. For a second, I will put you all to mute, because so now you're all muted, and I will continue the training again. So I have to go back to my. Yes, I'm sorry. It's very hard for me to keep everything in track. I have to share my screen again. Give me a second. Okay, so now we have to share screen again. from current slide. So we're back again. I have to set my chat to my colleague because my colleagues are there for you to see the chat. Okay, this webinar. There we are again. So questions are appreciated, but we have a lot of participants. Please keep your microphone muted. As we said, I just muted you all. You can unmute yourself. Please don't do it. You can raise your hand for a question and put it in the chat. That's the easiest way around. So we're talking about PESS. We as Lift Institute are 20-year experience inside PESS. And this webinar is basically for you to give you tools for your first PESS project, actually. Questions as what is PESS exactly? What kind of design consideration should I take? And how does the standard at all help me? A lot of people see the standard as a big obstacle, but when you understand how it works, it will actually help you. And this is the first. We will have 4 webinars. This, I will more or less talk about the concept of safety. And coming through these webinars, we go through how the standard really helps you creating better systems. So, PESS webinar 1, faults and how to handle them. First things first, I already said it a lot, PESS, but what does PESS actually mean? PESS is basically programmable electronic safety systems. And this is a lot, of course, but the first thing first, the system has probably software in it. The first word, programmable, means there is software running there. We can change the software. The second thing, electronical, means it's not mechanical. There are electronics involved in our system. And the last, safety system, it's a safety or a system that provides us some kind of safety. So PESS, programmable electronic safety system. So I see a lot of new people coming in. Please mute yourself again. It's really hard for me to keep focusing when I hear you all talking. Thank you so much. So, question for you, what is safety? Open your chat, please. Inside the chat, please give me some things. What do you think about safety? What is safety? What's the definition? What's it not? It has to do with something. Give me a small look to my moderator. If she sees people typing in the chat, don't be shy. Come on, you can just add something in the chat. Let me help you a bit. So the first thing a lot of people start talking about is harm. They want to avoid harm at some way. So it's protections against dangers. Thank you. So, but there's more. There's also some kind of likelihood. I really like this input. First presentation, I don't have that much chat input. Now we got a lot more. Thank you so much. Hazard. There's also some hazard. Eliminating something with hazards. Severity, because we want to have a low severity. Risks. I see risk in there as well. And a lot of times people talk about danger. And all these things are related to safety. It's very true. But it's not a real definition. I mean, the definition is very hard about safety. It's such a big, wide concept. So the good thing is we have standard. And standard tells us something like this. What is safety? Well, it's part of the overall safety related to the equipment under control, and the equipment under control, which depends on the correct functioning of the electric, programmable electronic system, safety-related system, other technology safety systems, and external risk reduction facilities. As you heard, this is a lot, and this is very clear, right? So this is problematic. We do a webinar about safety, and the first thing is what is safety, and it's not clear. So let me give you a different definition. A system is functional safe if failure do not lead into malfunctioning of the safety system and result in injury or death. So this is the most common, of course. For me, as mainly a lift person, we always want to avoid injured or deaf people. But also pollution of the environment. Safety systems is not typically only for lifts, it's also for very big machines, nuclear power plants, oil industry. And the oil industry really needs to avoid the pollution of an environment. If they have a big spoil of oil, we have a lot of problems in the world. And last but not least, the loss of equipment or production. So if we have a nuclear power plant and our system stops working for some reason, we don't have power anymore. And that can create a lot of risk as well. And last but not least, the safety function of a device has to be guaranteed under normal conditions, but also in the existence of faults. In the end, a safety function malfunctioning do not lead into problems, and it should be working always, normal conditions and faults. So let's dive into this a bit. I have the definition on top, and this definition gives off three very good questions. So the safety function of a device has to be guaranteed with the normal conditions and the existence of faults. This means, first of all, we have a safety function. And as you start a PESS project, a programmable electronic safety systems project, your first question will always be, what is my safety function? This definition is the key of a successful project. The second thing, so the first question, how is the safety function defined? The second thing is that we need to achieve or hold a safe state. We must be ensured we go to something safe. So the question then is, what is the safe state? For a lift, it's very easy. When we stop the car, it's stuck. People are safe in there. They don't move anymore. They don't get any harm. For a power plant, this can be something different. The last question is, how do we get there? So what are our temporary constraints? If we, for example, have a glass melting factory, their temperature is very important. If we have a lift, then speed is very important. And all that kind of variables should be taken into account. So the temporal constraints for the safety is very important. And if we answer these three questions first, then we have the blueprint of a successful project. So, for example, an overspeed governor. People in the lift industry, they probably know this. People who are not in the lift industry, this is a protection device against overspeed. How is this safety function defined? Well, we have to protect against something. So for an overspeed governor, our safety function is defined as protection against overspeed. And it's just as plain simple as that. But you should write this down. The second thing, what is our safe state? So we're protecting against overspeed. So our safe state for a lift, the car does not move. As soon as the car stops moving, we are safe. And last, what are temporary constraints? So I already told you a bit about this. We have something with time, of course, because if we have a short headroom or short pit, then the time is limited to stop the car. Speed is also linked to the time, of course, but the balance factor, the brake power, all those kinds of variables are very important. So now we have one safety function, and we see which kind of variables we have to enhance before we can really start our project. Again, the safety function of a device has to be guaranteed in the normal conditions, but also in the existence of faults. So then the questions arise, what are faults, basically? What kind of faults do we have? And the standard, the 61508, basically gives us tools for that. They separate faults as concepts in three big categories. Dear Goran, can you please mute yourself? And everybody double check if your microphone is muted. Thank you. Otherwise, I have to mute you all again, and then I have to stop the presentation. Again, we're talking about faults. Standard gives us three different kinds of failures. We have random failures, and each kind of failure I will explain a bit more. We have, with the random failures, is basically the lifetime of components. We have systematic failures, and systematic failures are software bugs, faults in specifications, all kinds of things which are basically wrongly engineered. And last but not least, the common cause failures. For example, temperature in the system. Let me explain you a bit more, but keep in mind we have three different kinds of failures. So first we dive into systematic failures. Systematic failures, it's management safety. Systematic failures are typically faults in software where you type your specifications wrong, and we can handle that very easily with documents. So a safety project always starts with a lot of documentation, but also reviews is a way for systematic faults to handle them. And in line of reviews, also notified bodies, as for example, Lift Institute, but also our competitors, are systematic fault measurements. So systematic faults are faults which are made by humans due to engineering activities, and we have to avoid them. The standard, which we handle most of the time, 61508, describes several techniques of avoiding systematic failures. And I understand this is it's a very difficult concept, so let me explain it a bit more by three examples. And in the meantime, you can think about it for yourself. How many errors, which percentage of errors do have a systematic cause overall? So let's first go to the examples. As we see over here, this is a satellite built by NASA. And this satellite was built for making pictures from Mars. And the nice thing about this project, this was one of the first projects combined NASA and ESA. And NASA had to create the satellite itself. And ESA created software. And English organization, they built the small rockets for steering. So the project started and everybody was very happy. And they launched the satellite. But this whole satellite never reached Mars. Actually, as soon as it got loose out of the space shuttle, it behaved very strangely and nobody understood why. So then they double checked everything and they saw very big problems in the calculations. What happened? In America, we used the imperial system, but in Europe, we used the metric system. And they did not decide which kind of systems they use. So the Americans always talked about imperial measures. And this means the software did not react properly because it was in metric. And that's one of the reasons that the whole trajectory of the satellite went wrong. And also the small booster rockets, which was built by the English, they were 4 times too strong. So this satellite never reached its goal, unfortunately, and it did cost us 327 billion, which is a lot of money. Another example. Here we see the ICE. This is a high-speed train developed and built in Germany. And it's very high speed, very high tech. And due to the enormous speed, you cannot open the windows. You will not open the windows at 300 kilometers an hour because you will probably be blown away by the amount of air. So there's an air conditioning in there. And imagine it's a sunny day, the sun is burning on your train, the air conditioning will go on. And they use some kind of cooling system which more or less stops working at 30 degrees inside temperature. But they decided the doors will be open at stops only, and the air conditioning will start working then, and no problem at all. So they built a train, And they had one small miscalculation. People hold the door open for each other. Due to that, the temperature raised more than 30 degrees. And at that point, the air conditioning stopped working. Nobody could have opened the windows, but the train still left. When they arrived at the station, it was more than 40 degrees inside the train, and it was a very big public scandal. So this is an example where we don't see the loss of money. Here we see really a public scandal. And last but not least, this example is the Patriot missiles. The Patriot missiles is an American weapon system, and they are made for interception enemy rockets. So they shoot down a rocket with their own rocket. And as we all understand, rockets have a very high speed. So the calculations are very important. And they tested it a lot, of course. However, there was one very, very, very small bug in the software, deeply hidden, and due to for our programmers on ROS, an integer overflow, a 32-bit integer overflow, in a very small chance, the calculation went wrong. And at that moment, the missile missed actually the rocket it had to intercept. And due to that, the enemy rocket hit 28 soldiers and they died. So this is a very tragic example of systematic failures, faults made by humans. So let's go to the next kind of fault. Please remember also the questions. What kind of percentage do have a systematic cause? Now you have more or less a better understanding what systematic faults are. Let me talk about random failures. So random failures. Random failures are basically failing of components. Components fail over time. We know everything breaks down at some point. And that's the reason why you see the image of the little bump with the timer. Each component is basically a time bomb of your system. It will break down. But when? And we don't know that exactly. However, the standard 61508 describes a mathematical way for calculating failures in your system. So this is an easier concept. And last but not least, this is a harder concept, common cause. So common cause failures are failures due to unexpected conditions. And very typical for common cause failures is one fault creates multiple errors in the system. So a fire, for example, can burn down multiple points of the system, and due to that, it behaves very badly. Also, we have a very big wave, for example, Fukushima. It's a very big wave, goes over a power plant. It was not expected. It's basically one earthquake, everything goes down. This is the typically common cause. 61508 provides us a mathematical way of dealing with common cause faults. Small question, should this be in a risk analysis? Well, yes, they should be there, but the problem is they are unexpected. If we expect them, they are not unexpected faults anymore, and they will then be in risk analysis, and then we have handled them because then we have eliminated them or dealt with them the proper way. So yes, you want to have them in risk analysis, but due to their nature, unexpected conditions, they are not. So remember the question, how much errors are systematic? Let me show you a very good image of this. Here we see that 44% of all faults in systems are due to specification. So we as humans create imperfect systems, and 44% of those faults in the systems are due to specification, and 15% is due to design and implementation. So 59% of all faults are human-made, actually. And 59% of all faults have a systematic cause. This source of this is Out of Control, which is a British investigation. And this gives us the value of document reviews, documentation, notified bodies. So now we've talked a bit about faults. We have seen there are 3 kinds of faults, and we have to handle them somehow because our safety system has to be guaranteed in normal conditions, but also in conditions with faults. So how do we handle actually these faults? Well, we have three main ways of handling faults. We can create fail-safe systems. We have diagnostics, and we have redundancy. I've seen raised hands. You can type in your question in the chat, and we will try to handle them in the end of the presentation. Thank you. So we can handle faults in 3 ways: fail-safe, diagnostics, and redundancy. And I will go point by point. It's always the computer who starts fighting back to me. There we go. So first of all, fail-safe systems. The basic thing about a fail-safe system is that it always goes to the safe state. So a fail-safe system always goes to the safe state. And a very good example is the brake system of a truck. The brake system of a truck is always pressurized, and when it loses its pressure, then the truck is stopped. As soon as somebody pushes the brake, then the pressure is released and the truck brakes. So when one of my hoses break for whatever reason, it doesn't matter. The system goes to a fully stopped state. And that's what we want. That's the safe state for our system. We also see the picture of the red emergency button on top. And we assume this is also a fail-safe system. Why? Well, the contact inside the system is a brake contact. So when we push the button, we break the contact. And even if the contacts inside the switch are welded, we are sure that we break the contact due to the mechanical construction. So whatever we do, we will always break the electric contact with this red button. Key thing about fail-safe systems is there is no single point of failure. Second thing, I invite you all again for the chat. Question of the day: what exactly is diagnostics? And I will look again to my moderator because he handles my chat. And let me see what's happening. So please use your chat. What do you think about diagnostics? In the meantime, I will double check that you're all muted again. So I see the first thing, fault finding. Thank you so much. State, yeah, that's very good. I'm doing 2 things at the moment, which is fault have to fail, yeah. So I muted you all again. Oh. So I see some checks. Check input out. Thank you very much. Very good. But also there's a measured value. We have to measure something. And people are expecting values as well. Exactly. That's true. And we have to ensure, yeah, ensure coming on and off. Thank you. So they must be in line with each other. Basically, diagnostics have 3 steps. So we have something we expect, then we check against it, and we act. So we measure something, we expect a value, we check if they are in line with each other, and if so, everything is good. If not, we stop our system. For you, I would like to show you the general safety concept of electronics. So most of the time, we see a relay key, down under. If this is turned on, our system works. And then we have contacts. When the contact is on, all contacts are on, our relay can perform and we can do our function. And if one of the contacts is broken, or if we break one of the contacts, the system will turn off to the safe state. So if all contacts are closed, we have power to function. This can be melt glass, this can be run the lift, this can be the chainsaw runs. And if one contact is open, so someone pushes emergency stop, the chainsaw stops, glass melting factory stops, etc. And all contacts in this line are fail-safe because we like fail-safe. Now we know this, I can talk to you about redundancy. So in the gray arrow, top to bottom, we have our safety system, our safety line. The output, again, is the relay. And we have our input, which is probably some kind of sensor, a microcontroller, so you see is a microcontroller, and they are connected to each other. At this point, I can switch off my system, but what happens when my output is broken? We all know relays do wear out quite fast. So we have to handle it at some point. And also my input has to be monitored. First, we check our output. So we'll read back the value of the relay. And if the relay is turning off and I turn it off, I know it works, everything is good. But the other way around, I try to turn it off, but I can see it doesn't turn off, I've got a problem. And in the current setup, I cannot handle this at all. So what do? Normally, we add a second output. So now I got two relays. Normally I switch on and off my first relay, the blue one, or this can also be a FET, by the way. And if that relay doesn't react to my comments anymore, I simply switch off the second output module, the orange one. But there is a new problem rising up because the orange relay or output module is always on. So as soon as I turn it off, I'm not sure if it works. So I put a readback loop in there as well. So at this moment, I got two output modules controlled by one microcontroller. And this seems to be pretty okay. But we all already saw that 65% of all faults are due to systematic errors. And software is human-made, so software faults are systematic. So what do? We create a watchdog to monitor our microcontroller. And at this moment, I can check if the microcontroller still runs. And a watchdog is nothing more than a small control loop. Are you still running? Yes, you can still run. And if you do not run anymore for whatever reason, so the software hang, we will reset you. And that's an increasement of safety, but it also gives a problem because this watchdog cannot perform the safety function itself. So the next easy upgrade, you just don't put there a watchdog, you put there a complete microcontroller. And this microcontroller is capable of switching off the output. And now the microcontroller is fully monitored. It also monitors the output again. I become a lot safer. Next step, of course, is to create a double input. So all my inputs are read out by my microcontrollers. Microcontrollers, they check each other, and they also check the output stage. And now we have a fully redundant system. So it doesn't matter where I demolish. So I can demolish a blue input. My orange input will still be there. I can wreck a blue output. It doesn't matter. It doesn't really matter which block I break down. System still reacts properly and can go to the safe state. So this is redundancy. Just put a double pair of systems over there. I want to talk a bit more about monitoring and diagnostics because we have two ways of monitoring. We can monitor things static or dynamic. For example, when I switch off an input sensor and I got still signal of my input, something is going wrong. So now in a coronavirus, me, for example, I do take a lot of my temperature, my body temperature, and it always gives me 36.5 degrees, which is perfect. But the system can be broken. So what I should do is first I measure my own temperature. It gives me a value which I like, I hope. And then I measure just the plain air. If it still gives me the 36.5 degrees, I know something is wrong because I expect something else. And this whole strategy I can do with all kinds of sensors. If I measure the pressure, we see the pressure sensor in the image, I can switch off the supply of this sensor and double check if I get still some input. If not, then my electronic circuitry is good. If I still get some value, something is going wrong. And this we call dynamic monitoring, and it's a real improvement of your system. Well, I already told this more or less. Do we do the same for relays? Well, yes, and in elevators, we already do this a lot because in elevators, we do flank control, which is basically just double check, did it really switch off and did it really switch on? So dynamic monitoring is a better way for your diagnostics. So now we go to a small conclusion, and then I got some questions, of course, because I like those. First things first, safe systems are always predictable. Well, why? Because they always go to the safe state. So it doesn't matter what happens, they are predictable, they go to a safe state. We have three kinds of errors with their own heuristics. For if you remember, we have the common cause, we have the systematic errors, and the random errors. Most of the errors are introduced in the development. In the specification and the development, 59% of all faults of systematic cause are coming up there. And with several tactics to avoid unsafe situations. So we had the diagnostics, we had the redundancy, and we had the fail-safe. And just an extra from me to you, diagnostics are a very popular and trustable way to improve your system. And if you use diagnostics, they should be dynamic. I have two questions for you, and I'm not going to answer these questions in this webinar. I will do this in the second webinar, which is next week. So safe systems are predictable because they go to safe states. But how do I prove that the system is predictable? How do I prove it? And the second thing where you can think about, how do I express safety? So next webinar, I will completely tell you everything about this. For now, we go to some examples / questions. I will continue with 3 questions. Each question will be fully explained. Please do not use the chat for the answer. I will do the full discussion by myself. We just have too many people in here. So when the first computer was created, we had a real bug. There was a muff flying into a relay, and it created a short circuit. And this short circuit just basically wrecked the computer. What kind of fault is this? So we had the 3 options. We had random failures. And if you think about random failures, it's more or less the lifetime of components. And this has nothing to do with the lifetime because some external thing demolished my system. So a random failure, it's not. Then we have a common cause. Well, there is one muff and it created one fault in one relay. So it's not really a common cause failure as well. Then the last, the systematic failure. Well, could we have avoided it that this muff were flying in? Yes, we can put something for the window, for example, to make sure no dirt or animals go in. And if we did that, we have fully avoided this failure. So this first real bug, this real computer error was created, was the systematic failure. So the next one, this one is a real good discussion as always. Airplane crashes in general. What kind of faults are these? So we have a lot of airplanes flying around, and they are actually very, very, very safe. However, sometimes we do have crashes, and they are investigated really good, and that gives us the tools and a lot of information what did go wrong. So you also have to know airplanes who have a really tight maintenance schedule. Everything is replaced before they are worn out at all. And that means that we avoid random failures more or less. And if you have ever watched air crash investigation, you will always see that it's not due to worn out materials. So then we have systematic faults. Systematic faults were due to our engineering. And from time to time, we have a systematic fault, but they are very small because our investigations, we see what we did wrong and we improve it. Also, a certification project for an airplane is very long and very hard to achieve. So we already have a lot of measures to avoid this kind of faults. Then we have the common cause. So what we see most of the time is that something is broken in the aircraft due to lack of maintenance. Then the pilot reacts to it, but not on the proper way, or he makes the second fault. And these faults combined end up in a crash. So most of the faults in airplanes are some way systematic or common cause. It's always a gray area in between that. We fully excluded the random failures due to the maintenance schedules. And last but not least, yeah, I had to do something with the windmills, of course. We have a nuclear power plant. In the Netherlands, we have 3 of them. And at once, the nuclear power plant, it turned himself off. It did go to the safe state. It stopped the whole nuclear process. And it reaches newspaper, of course, with the big question, is this plant still safe? Well, yes, actually, it's a good thing it turns itself off because the safety system detected something what it should not be, and it reacted in a proper way. It did go to a safe state. Think about what happened if the system did not react like this. So it's perfectly safe, actually. It's how we designed it. But now, the same nuclear power plant turns itself off every week. Is this still safe? Well, at this point, the discussion starts. Because on one hand, yes, the safety system works, and that's perfectly fine. But on the other hand, if every week your safety function is triggered somehow, your normal control loop is misbehaving, or your design is probably not fully right. There is more going on than you expected, because you don't expect the system to go to the safe state each week, especially not for nuclear power plants. And also, when you go to the safe state, most of the time you wear out a bit faster than you should normally do, because you want to go to the safe state fast. If the nuclear power plant turns itself off every week, I should have some doubts about safety, and probably an investigation should start. So that's it for today. Thank you so much for your attention. I would like to tell you one thing. This webinar is intellectual property of the Lift Institute. So if you think it somehow, please, it's intellectual property of the Lift Institute. That being said, if you have any questions, you can put it in the chat now. My moderator will select some questions. In the meantime, we have a second webinar on the 12th May at 3 o'clock as well. There I'll tell you more about safety integrity levels and how we measure safety and how we can handle them. Third webinar, it's also 3 o'clock, 26th of May. There we talk about the bigger picture of functional safety, which is more or less the interconnection between standards. And the fourth webinar is June 9th at 3 o'clock as well. And there we handle FMEA's failure modes and effect analysis, and how to apply this analysis in the elevator industry. Give me a second. I have a sip of water, and then I look to my moderator if you got any questions inside the chat. So thank you again. I have one question which I can just, one thing I will discuss with you because I like this example. In the last presentation, I got a question where somebody said, I have a transistor in my system and there's a lifetime of 20 years in the data feed. And these 20 years is actually never met. Actually, in 4 or 5 years, it's always that component who breaks. And I don't understand it. What kind of fault is this? So the first thing you have to ask yourself, is my environment secure? Are they correct? Do I run it on a proper temperature? Is there a lot of dust in there? Is everything according to specification? And if not, you have a systematic failure. You have a wrong design thing going on. And if it just simply breaks down and everything is within its limits, then you have a lot of random failures. But then for the manufacturer of the components, it's a systematic failure because his system somewhere in production is not good. And I really like this example because on one hand, we have random failures. On the other hand, it's also a systematic failure. So it really makes clear that everything is connected some way to each other. So, yeah, I don't see any questions anymore in the chat. Thank you so much. I will stop this presentation. I hope to see you all next week, the 12th, 3 o'clock. And we will all send you a new link for this one. So that's it. I'll go to mute.